Welcome to Statistics, where we bring complexity to clarity. I'm excited to have you join me for our 8th unit, Measures of Dispersion. Here you can see that there are 4 series with different observations. Can you guess the mean for each? Well, you guessed it correct. It is 4, same for all the series. So here comes the role of measures of dispersion. What do you mean by dispersion? Dispersion can be defined as the extent of scatteredness of observations around a measure of central tendency, and a measure of such scatter is called measure of dispersion. Let's see it with the help of example. Let's consider series 1. Here the observations are 2, 3, 4 and 7. You may be thinking why I have written them so scattered. So that's the answer. To see the scatteredness of them with respect to its mean. So we can see that the first observation is scattered by 2 units from its mean. The second observation is scattered by 1 unit. And the third observation is scattered by 0 units as it is same as the mean. And the fourth observation is scattered by 3 units from the mean. So, dispersion tells us about the scatteredness of each observation from the mean, that is its central tendency. So, this is the reason to study measures of dispersion in order to have an idea of the data set. Now, let's see different measures of dispersion, like range, absolute mean deviation or absolute deviation, standard deviation, variance, standard error of mean, and coefficient of variation. We will be discussing them in detail. An ideal measure of dispersion should possess all those characteristics which are considered essential for measures of central tendency, namely, it should be based on all observations, it should be readily comprehensible, it should be easily calculated, it should be simple to understand, it should not be affected by sampling fluctuations, it should be amenable to algebraic treatment. So these are the requisites or characteristics of an ideal measure of dispersion. Now let's see the first measure of dispersion, range. Range is the difference between the highest and the lowest values of the observations or data in a given distribution or series. For example, here we have 3 series. Now, in the first series, the highest value is 7 and the lowest is 2. So, the range will be 7 minus 2, that is 5. In the second series, the highest value is 12 and the lowest is 1. So the range will be 12 minus 1, that is 11. And in the third series, as we can see, all the observations are same. Hence, the highest and lowest values are same. So the range is 0. Since range depends on the highest and the lowest values in the distribution or series, as such, it is very unstable measure and is affected by sampling fluctuations. However, its concept is simple and easy to calculate. Now let's see the second measure of dispersion, that is absolute mean deviation or simply absolute deviation, abbreviated as AMD. The sum of deviations of all the observations from the arithmetic mean without any positive or negative signs are known as absolute deviations, and the mean calculated from these deviations is called absolute mean deviation. If the deviations are calculated from arithmetic mean, then it is called mean deviation about the mean. Let's see the formula of it. For ungrouped or raw data, AMD is equal to summation I is equal to 1 up to n modulus xi minus x bar upon n, where xi is the variate value, x bar is the mean, and n is equal to number of observations. For grouped data, AMD is equal to summation I is equal to 1 up to k fi modulus xi minus x bar, divide by summation fi, where fi is the frequency of ith class and k is number of classes. Here in the formula for grouped data, we just need to put the fi term in the formula for the ungrouped data. So that's the difference. Now let's see the third measure of dispersion, that is standard deviation. It is the square root of the ratio of sum of square of deviation calculated from arithmetic mean to the total number of observations minus 1, which can be written as the square root of the ratio of the sum of square of deviation of each observation from its arithmetic mean to the total number of observations minus 1. It is based on deviation from arithmetic mean and is denoted by small s for sample and sigma for population. The standard deviation or root mean square deviation is the most common and efficient estimator used in statistics. Different methods of computation for standard deviation are as shown. For raw or ungrouped data, we can calculate standard deviation using deviation, variable or assumed mean method. And in grouped data, we can calculate it using deviation, variable, assumed mean or step deviation method. Let's see them in detail. The formulae for calculation of standard deviation for raw or ungrouped data are as follows. According to deviation method, standard deviation is equal to square root of summation I is equal to 1 up to n xi minus x bar square divided by n minus 1, where I is equal to 1, 2, 3 up to n observations, x is equal to variable value, and x bar is equal to arithmetic mean. According to variable square method, standard deviation is equal to square root of summation I is equal to 1 up to n xi square minus summation I is equal to 1 up to n xi square divided by n whole divided by n minus 1. And according to assumed mean method, standard deviation is equal to square root of summation I is equal to 1 up to n di square minus summation I is equal to 1 up to n di square divided by n whole divided by n minus 1, where di is equal to xi minus a and a is equal to assumed mean. Now let's see the formulae for grouped data. Deviation method. Here the formula is same as that for the ungrouped data, except we add the term fi, and fi is the frequency of ith class, xi is ith class mid value, and k is equal to number of classes. Similarly, in case of variable square method also, we add the frequency terms at these two places in the formula for ungrouped data. So we get the formula of variable square method for grouped data. Similarly, in case of assumed mean method also, in the formula of ungrouped data, we add the fi frequency terms at these two places to get the formula for grouped data. And in case of step deviation method, standard deviation is equal to root of summation I is equal to 1 up to k fi dxi square minus summation I is equal to 1 up to k fi dxi square upon n whole divided by n minus 1 into I. Here dxi is equal to xi minus a upon I. I is the class interval. Fi is the frequency of ith class. K is the number of classes. Now let's see the properties of standard deviation. The first property is combined standard deviation can be calculated using following formula when two series are given under study. It is symbolically denoted by S12. S12 is equal to root of n1 into s1 square plus d1 square plus n2 into s2 square plus d2 square whole divided by n1 plus n2. Here S12 is the combined standard deviation. S1 and S2 are the standard deviation of first and second group. D1 is equal to x1 bar minus x12 bar. D2 is equal to x2 bar minus x12 bar. N1 and N2 are the number of observations for series 1 and 2. x1 bar and x2 bar are arithmetic mean for first and second series. x12 bar is the combined mean. The second property of standard deviation is the sum of squares of the deviations of items in the series from their arithmetic mean is minimum. This is the reason why standard deviation is always computed from the arithmetic mean. Let's see it with the help of example. Here we have the series xi with observations 7, 8, 8, 10 and 12. The mean of the series is 9 and its median and mode is 8. So here the sum of square of deviations of the items in the series from the arithmetic mean is 16 and from median is 21 and from mode is also 21. So as 16 is less than 21, it satisfies the property. Now let's see the third property of standard deviation. It says that addition or subtraction of a constant to each observation of the data set will not change the value of standard deviation. For example, taking the series with observations 7, 8, 8, 10 and 12 and on adding a common constant 2, we get the new series. Here the standard deviation of the original series is root of 16 by 4, that is 2, and the standard deviation for new series is equal to root of 16 by 4, which is 2, thus satisfying the property. You can also check the same by subtracting a constant from each observation and see the results. From this, we can say that standard deviation is independent of origin. That is, adding or subtracting a constant to each observation of the data set does not affect the standard deviation. Now let's see the fourth property of standard deviation, that is multiplying or dividing each observation of a given series by a constant value will multiply or divide the standard deviation by the same constant. Let's see it with the help of example. Again we have the series with observations 7, 8, 8, 10 and 12. Here we multiply a common constant, say 2, to all the observations and get the new series as shown. The standard deviation of the original series is root of 16 by 4, which is equal to 2. And the standard deviation of new series is equal to root of 64 divided by 4, which is equal to 4. So according to the formula, the new standard deviation is equal to the original standard deviation into the constant multiplied, that is equal to 2 into 2, which is 4, thus satisfying the formula. Similarly, you can divide each observation of the given series and see the results. From this, we can say that standard deviation is dependent on scale, that is, multiplying or dividing each observation in a given series would affect standard deviation. If all the value of series are same, then standard deviation will be Now, let's see the fourth measure of dispersion, variance. Variance is the square of standard deviation. It is also called the mean square deviation. It is being used very extensively in analysis of variance of results from field experiment. Symbolically, it is denoted by S square or SD square, where small s square for sample variance and sigma square for population variance. The different methods for computation of variance are as shown. For raw or ungrouped data, we can calculate variance using deviation, variable or assumed mean method. For grouped data, we can calculate variance using deviation, variable, assumed mean or step deviation method. Let's see them with formulae. The formulae for calculation of variance for raw or ungrouped data are as follows. According to deviation method, variance, that is s square, is equal to summation I is equal to 1 up to n xi minus x bar square divided by n minus 1. Yes, you guessed it correct. It is similar to the formula of standard deviation because we know that variance is the square of standard deviation. Hence, squaring the formulae of standard deviation, we get the formulae of variance. So, here we just need to remove the root sign in the formula of standard deviation. Similarly, for variable square method also, we have to square the formula of standard deviation, thus removing the root sign will give the formula of variance. Similarly, for assumed mean method. Let's see for grouped data. According to deviation method, the formula is again same as standard deviation. We have to square the formulae of standard deviation. Thus, the root sign will be removed. Or, as we know that in case of grouped data, we just need to add the frequency term here in the formulae of raw data. And same for variable square method. We can get it by the square of standard deviation formulae, that is, the root sign will be removed, or we can get it from the formula of ungrouped or raw data by adding the frequency terms at these places. Similarly, for assumed mean method also, we get the formula by squaring the formula of standard deviation, or by adding the frequency terms at these two places in the formula of ungrouped data. For step deviation method, we can get the formulae of variance by squaring the formulae of standard deviation. That is, the root sign will be removed from the formula of standard deviation and we get the formula of variance as shown. Now, let's see the properties of variance. The first property is combined variance can be calculated using following formula when two series are given under study. It is symbolically denoted by S12 square. Here S12 square is equal to N1 into S1 square plus D1 square plus N2 into S2 square plus D2 square whole divided by N1 plus N2. Here S1 square is variance of first group, S2 square is variance of second group, D1 is equal to x1 bar minus x12 bar, D2 is equal to x2 bar minus x12 bar, N1 and N2 are the number of observations for series 1 and 2. X1 bar and X2 bar are arithmetic mean for first and second series respectively. X1 bar is the combined mean. Now, let's see the second property of variance. If Vx represents the variance of X series and Vy represents the variance of Y series, then variance X plus Y is equal to Vx plus Vy plus 2 covariance Xy. And Vx minus Y is equal to Vx plus Vy minus 2 covariance X minus Y. Let's see the example of variance of X plus Y. Here, the series X has observations 7, 8, 8, 10 and 12 and series Y has observations 2, 3, 4, 7 and 9. Series Z, which is made by the summation of the observations of series X and Y, that is 7 plus 2 equal to 9, then 11, 12, 17 and 21 respectively. Series X has variance 4, for Y 8.5, covariance XY is equal to 5.75. Now, in the property, putting the values, we get 4 plus 8.5 plus 2 into 5.75, which is equal to 24. Thus, satisfying the property. Similarly, you can check for Vx minus y. Now let's see the third property. Addition or subtraction of a constant to each observation of the data set will not change the value of variance. Let's see the example. We have the series X with observations 7, 8, 8, 10 and 12. Here we are adding a common constant 2 to all the observations and get the new series as follows. The variance of the original series is 16 by 4, which is equal to 4, and the variance of the new series is equal to 16 by 4, which is equal to 4, thus satisfying the property. Similarly, you can check by subtracting a constant from each observation and see the results. From this, we can say that variance is independent of origin. That is, adding or subtracting a constant to each observation does not affect variance. Now, let's see the fourth property of variance. Multiplying or dividing each observation of the data set by a constant will multiply or divide the variance by square of that constant. For example, Vax is equal to a square Vx. Here Vax is the new variance and V of x is the original variance and a is the constant. Let's see the example. Suppose we have series X with observations 7, 8, 8, 10 and 12 and we multiply it with a common constant 2, then we get the new series as follows. The variation, or we can say variance of the original series is equal to 16 by 4, which is 4, and the variance of the new series is 64 by 4, which is equal to 16. So, putting in the formula, we get the new variance is a square into the old variance, that is 2 square into 4, which is equal to 16, thus satisfying the property. You can check the same by dividing each observation of the data set and see the results. So from this we can say that variance is dependent of scale, that is Multiplying or dividing each observation would affect the variance. Now let's see the fifth measure of dispersion, that is standard error of mean, SEM. It refers to the average magnitude of difference between the sample estimate and the population parameter taken over all possible samples from the population. Or it is defined as the square root of the ratio of the variance to the total number of observations in a given data set. That is square root of the ratio of the variance to the total number of observations. Symbolically, it is written as Sx bar for sample and sigma x bar for population, or Sx bar is equal to S upon root n. Now let's see the sixth measure of dispersion, that is coefficient of variation, CV%. It is a relative measure of variation and widely used to compare two or more statistical series. The statistical series may differ from one another with respect to their mean or standard deviation or both. Sometimes they may also differ with respect to their units, and then their comparison is not possible. To have a comparable idea about the variability present in them, CV% is used. It was developed by Carl Pearson. CV% is a percentage ratio of standard deviation to the arithmetic mean of a given series. That is, we can say that the percentage ratio of the standard deviation to the arithmetic mean. It is without unit or unitless quantity. CV% is equal to S upon x bar into 100. The series for which the CV% is greater is said to be more variable or less consistent, less homogeneous or less stable, while the series having lower CV is called more consistent, more homogeneous or more stable. Thank you for joining me on this journey through our 8th unit, Measures of Dispersion. If you found this unit helpful, don't forget to like, share and subscribe to Statistics for more insights and clarity on statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.